You probably know that you can make water flow faster by decreasing the size of the opening it goes through. In this video, we're going to try to figure out why this is. The first thing we need to understand is how differently the two common fluids that we're exposed to, air and water, behave when they're compressed. Let's take a look as I try to compress these two fluids. So I've got here a soda bottle, a mallet, and some water. We're going to use this water to break the soda bottle. You wouldn't think water would be very threatening to a soda bottle. After all, soda is basically water. But because of the incompressibility of it, it's not that hard to break the bottle. Now I have to show you what I mean. Okay, so this bottle's empty. And if I just hit it really hard with the mallet, nothing happens. So if we think about what was going on in that bottle, it was just full of air. And air molecules have lots and lots of space between them. It's mostly nitrogen and oxygen. They don't interact with each other very much. There's very few intermolecular forces. So air is a fluid that's inherently compressible. If you start to put pressure on the top, if you start to jerk the bottle around, these molecules can just move around. And that's why nothing really happens. That's very interesting. In the case of water molecules are not really free to move around because there's that tight hydrogen bond network where the hydrogens of one water molecule are attracted to the oxygen of the next. So water is much more constrained in how a single molecule moves. We're going to see that it's not compressible. Let's take a look at the consequences of that. Let's put a little water in. And now we'll repeat the experiment. And hopefully I won't drop it. There we go. So what's happening here? I'm using this demo to demonstrate that water is an incompressible fluid, and the demo certainly shows that. But the actual cause of the bottle breaking is something we didn't understand very well until recently. Believe it or not, this is something that's been actively researched in this decade. If it was 5 years ago, what I would tell you is that the bottle broke because of Pascal's principle. That essentially, because I put a force on the water in the narrow neck of the bottle, which had a low surface area, the bottom of the bottle, which had a much larger area, because the pressure was the same at the top and bottom, that meant a much larger force had to be present on the bottom of the bottle. In the early 2010s, people using high-speed photography realized that the story was a little more complicated. And they realized that what was happening was something called cavitation. So, basically, when you whack the bottle with the mallet, the bottles go shooting down. And that leaves an area next to the bottom edge of the bottle that has very, very low pressure. In the case of the air, molecules can just kind of gently filter in. The air fluid is very compressible. It doesn't matter if it changes its volume. In the case of water, though, the atmosphere pushes that fluid, basically atmospheric pressure, into the bottom. It's very weird to watch this in high-speed photography. The bubbles form, and then faster than they form, all the water goes shooting down into it. That's what cracks the bottle. This is something ship designers have to pay attention to, because this could cause serious damage to the bottom of ships. But at the end of the day, what I wanted you to get out of this is that we can't compress water. That's going to help us understand what's going on with the water coming out of the faucet. So now I'm going to try to walk you through the math you need to understand why water speeds up on a faucet when you put your finger over it. One thing I want to say before we get started on this math is a source of confusion is volume is a capital V and velocity is a lowercase v. So just keep that in mind and try to really exaggerate that in your own problems. Let's take a look at this math. So hopefully we agree now that water is incompressible, and it's because of the forces that water molecules put on each other. If I put a heavy weight on a plunger on top of a volume of water, the volume's not going to change because the water molecules are not going to allow themselves to be pushed together. Now imagine I'm putting that water into a pipe. I'm going to put a certain volume per second at this end. Since water is incompressible, in that time period, the same volume should come out the other end. So it's not just volume that's the same, it's the volume flow rate. The number of cubic meters per second should be constant at every point in this fluid. That's really what's going to help us understand why water speeds up when you put your finger over a faucet. So the best way I have to justify the equation we're going to come up with is to use unit analysis. So hopefully we can agree that volume is measured in cubic meters, and volume flow rate would just be the speed of cubic meters, or cubic meters per second. Let's just play around with the equations a little bit. Again, because water is incompressible, the volume flow rate at this end of the pipe should be the same as that at that end of the pipe. So hopefully this part makes sense. Volume has the unit meters cubed, time has the unit seconds. So we have meters cubed per second on both sides. I'm just going to break the meters cubed into two terms. And the reason I'm doing this is I end up with meters per second when I pull a meters out of meters cubed. Meters per second, of course, is the unit for velocity. And so we're talking about how fast water comes out of a pipe. Velocity is something kind of interesting. So this ends up getting velocity into our equation. And meters squared is the unit of some sort of area. What area is it? It's the cross-sectional area, in other words, the area of this circle at either end of the pipe. Since this pipe has a constant area on either end, the pipe has the same diameter, we expect the water to stay the same speed throughout that pipe. But in the case of a pipe where the diameter changes, the cross-sectional area is going to change too. And that's going to make water speed up or slow down in different parts. If this equation is still true, if the area gets bigger, the speed has to drop. If the area gets smaller, the speed has to increase. And that's why putting your finger over the pipe makes the water speed up. You're decreasing the effective area that water can go out of. So in order to maintain the constant volume flow rate, that means the water has to travel faster. All of this stems from the fact that water is incompressible.